we are from SMA 1 Palangkaraya. My name is Helena Kristasterin and my partner name
Jesiana Maria.
We are one of the team that participate in Lomba Peneliti Belia Nasional 2020 in physics categories. As young researchers, we are going to present our research about how a small-scale lightning power plant works.
Let's watch our video. Power plant is an industrial facility that produces electrical energy from renewable and non-renewable energy sources. Lightning offers the potential difference between cloud and earth, or cloud and the other cloud. Potential difference causes the removal of electrons in order to achieve equilibrium, which in theoretical can be used as a source of electrical energy. In energy crisis condition, the non-renewable energy can no longer be used to fulfill human needs. So, renewable energy is needed to overcome energy crisis.
Currently, research related to the use of lightning voltage as a renewable energy sources in the future is still being developed by various researchers around the world and has not found a clear point of evidence regarding to the existing theories. As a young researchers, we are interested to continuing our research experimentally based on our previous paper.
Lightning catcher circuit. The lightning catcher is made from the following components. 1. Copper pipe, which is connected by a copper cable as a conductor of high voltage from artificial lightning to the capacitor. 2. Iron pipe, which works as a grounding component. 3. Neodymium N52 magnet, with a function to focus a lightning strike directly onto the copper pipe. 4. Insulator, which needed to ensure the iron pipe remains as grounding component. 5. Copper cable, which is connected respectively to the copper pipes and iron pipes. The red cable is used to connect the copper pipe, and the black cable will be connected to the iron pipe as the grounding component. And then, we are going to the design of the voltage storage. First, design of artificial lightning voltage storage. As the first simulation, we directly connected the artificial lightning catcher to 30 pieces of 50V and 1000 microfarad electrolytic capacitors, which arranged in parallel. Second design of artificial lightning voltage storage. As the second simulation, we connected the artificial lightning catcher to an artificial electrostatic capacitor. This electrostatic capacitor is made from a plastic map folder and aluminum foil, which is rolled together. We used 3 electrostatic capacitors, which had 8.07 nanofarad capacitance after being parallel. Third design of artificial lightning voltage storage. As the third simulation, the artificial lightning catcher connected to the capacitor through RGB63K2 plasma IGBT. In our previous design paper, we chose to use the IRGB-C40S type of IGBT, but that's too small to hold the high voltage. Researchers hope that the IGBT could reduce the high voltage and increase the current. The IGBT connected to the circuit as this following schema. Fourth design of artificial lightning voltage storage. As the fourth simulation, the artificial lightning catcher connected to the capacitor through high voltage resistor and RGB63K2 IGBT. The resistor and IGBT connection with the circuit can be seen in the following schema.
The voltage contained in the plasma was 629,000 volts. This proved that both artificial and real lightnings had a potential difference that appeared in the voltage measurement results. This result saw how lightning can be captured by the lightning catcher. The red cable was connected to the copper pipe, and we found that the voltage has decreased from 629,000 volts to 47,000 volts.
Each voltage measurement was done by analyzing the voltage stored in the capacitor. The capacitor was considered unable to store because the measurement result was 0 volt. The reason why the capacitor could not store the voltage was because the electricity from the Tesla coil as artificial lightning with static electricity, not current electricity.
At the top of the lightning catcher, there is a magnet which has electromagnetic waves. The electromagnetic waves can attract the lightning strike towards the copper pipe. From the copper pipe, the voltage will apply through the red-colored copper cable. The iron pipe and the copper pipe are connected with an insulator between them. The iron pipe works as a grounding component. At the first simulated design, the red-colored copper cable from the copper pipe is connected to the positive polar of electrolytic capacitor. The black-colored copper cable is connected directly to the negative polar of the electrolytic capacitor. At the second simulated design, the red-colored copper cable and the black-colored copper cable are connected directly to the electrostatic capacitor without determining the poles first, because the electrostatic capacitor didn't have any poles like the electrolytic capacitor did. At the third simulated design, the red-colored copper cable is connected to the emitter pin of the IGBT, which will collect the electrons before they are distributed to the gate pin and the collector pin. The black-colored copper cable is connected to the gate pin of the IGBT, and then goes to the negative polar of the electrolytic capacitor and also act as a grounding component. The collector pin is connected to the positive polar of electrolytic capacitor. At the fourth simulated design, the red-colored copper cable and the black-colored copper cable are connected to the high-voltage resistor before going through the IGBT. The high-voltage resistor is made by N52 neodymium magnets with 1 cm diameter and length. Between the magnet, there will be given an insulator, and the rest of the circuit will be just the same as the third simulated circuit. The high voltage in the lightning is still in form of static electricity, not a current electricity. So it's very difficult to stop the voltage in a capacitor. As young researchers, we have tested 4 designs of lightning voltage storage, and none of them have succeeded to stop the voltage. The result obtained is how can be a reference or theoretical basis for the next researchers. Thank you.
In this study, we were able to prove through a small-scale simulation, lightning can be captured by using a lightning catcher. However, there are difficulties in storing this high voltage in the capacitor. This is because the voltage contained in the lightning is still in the form of static electricity and is not current electricity. Our future plan related to this research is to research more about how to convert the static electricity into the current electricity. Stop. In addition, this research is still simulated in a small-scale system. So if it is applied in real life, the researcher cannot guarantee it will be safe because we can ensure the copper material can resist 1 million kilovolt of the voltage that the real lightning has. The challenge was the storage circuit was unable to store because a lightning strike was too fast, less than a millisecond.
Thank you for your attention.